The Carnot engine and the second law also give us the concept of an absolute temperature scale, which is essentially a temperature scale which is independent of the working substance. So, let us say we have some temperature reservoir, let us say it is high temperature T1, some low temperature at T3. I can run a Carnot engine between T1 and T3 and get out some work Wc. So, this takes Q1 amount of heat, rejects Q3 amount of heat and gives me a net work of Wc. So, the efficiency of this Carnot engine would be 1 minus whatever is the heat rejected divided by the heat which we give in. So, we saw this earlier. So, we saw that from the first law Wc is essentially Q1 minus Q3, efficiency is W by Q1, W by whatever heat you add, and W is Q1 minus Q3. So, we have efficiency as this. So, we said this is essentially 1 minus Q3 by Q1, that is efficiency. So, essentially what we see is that our efficiency is 1 minus the heat transferred at the lower temperature divided by the heat transferred from the higher temperature. So, 1 minus the heat transferred by at lower temperature divided by heat transferred at higher temperature. So, this would be the efficiency of this Carnot cycle operating between T1 and T3. Now, what I can also do is I can operate two other Carnot cycles with some intermediate temperature reservoir in between. So, this transfers heat, takes Q1, does some work Wa and rejects some Q2. This Q2 is given to this next heat engine B. It takes heat at Q2, gives some work of Wb and rejects heat at Q3. So, if I took the efficiency of this Carnot engine, what I would get is that the efficiency of this is essentially 1 minus Q2 by Q1. The efficiency of this engine would be 1 minus Q3 by Q2 in the same fashion. So, what I can see is that if I run this engine and I run this in a sequence of engines, finally whatever I should get, the efficiencies should be the same. So, and in all of these cases whatever I see is that the ratio of the heats transferred, they have to be only functions of the temperatures, because that is essentially what Carnot says. Carnot says that if I have two temperature reservoirs, if I run a Carnot engine, if I run any Carnot engines between them, the efficiencies are only functions of these two temperatures and of nothing else in between. So, the efficiency here is 1 minus Q3 by Q1, which has to be some function of T3 and T1 or T1 and T3 according to Carnot. So, if 1 minus this is a function of this, then Q3 by Q1 also should be a function of this. So, Q1 by Q2, which is related to efficiency of this engine, is a function of T1 and T2. Q2 and Q3, which is a function of the efficiency of this engine, is a function of T2 and T3. Q1 and Q3 is a function of T1 and T3. So, what we see is the ratio of the heats transferred by these intermediate engines are functions of the temperatures of these intermediate engines, whereas if I use a single engine, the heat transferred here is a function only of these two. So, I have Q1, Q2, Q2, Q3, Q1, Q3. I can multiply this. If I multiply Q1 by Q2 into Q2 by Q3, I will get Q1 by Q3. Okay. So, what I can do is I have the first engine, I have Q1 by Q2, which is a function of efficiency. This is a function of T1 and T2. For the second engine, this engine, I have Q2 by Q3 gives me 1 minus Q2 by Q3 gives efficiency, which means Q2 by Q3 is a function of T2 and T3. For this big engine, I have the efficiency as 1 minus Q1 by Q3, which is a function of T1 and T3, which means that Q1 by Q3 is a function of T1 and T3 according to Carnot's theorem. So, this Q1 by Q3 should be a function only of T1 by T3, and I can also write this as Q1 by Q2 into Q2 by Q3, which means this is a function of T1 T2 into a function of T2 T3. So, this function of T1 T2 into a function of T2 and T3 should be finally a function only of T1 and T3. So, I have two functions which I multiply. If I multiply this, I should get it as function of only 1 and 3. So, for example, if I call this some x, y and z, I have some x and y, some function of x and y, some function of y and z, and this is some function of x and z. So, essentially what I do is, if I multiply these two, the y's should cancel out. So, if I want this kind of a function, so what is required is that these are individually functions in the denominator and numerator. So, this must be some function of some T1 divided by function of some T2 such that, and this must be some function of some T2 divided by some function of some T3 such that when I multiply these get cancelled out and I get some function of T1 and T3. So, that is essentially what follows from this, which is essentially what Kelvin realized. So, Kelvin realized that if I have this function of T1 and T3, since all of these are consistent, this function must be of the form of T1, some function of T1 divided by some function of T3. So, what he found is that Q1 by Q3 is essentially some function of T1 divided by some function of T3, or QL by QH is some function of TL by some function of TH. So, what he assumed is that Q1 by Q3 is essentially T1 by T3 itself. This is what Kelvin assumed. He said, instead of finding out some function, let me assume that this function is in this form. So, if you assume that it is in that form, it gives us essentially some kind of a temperature scale. So, if you have a Carnot engine which you run between like two temperatures, then the heat transferred, the ratio of the heat transferred are linked to the ratio of the temperatures, which is what we saw. If I have a Carnot engine running between two temperature reservoirs, the ratios of the heat transfers are linked to the ratios of the temperatures. So, I can now think of running a Carnot engine between temperature reservoirs of different temperatures. Finally, I reach some temperature of 0 somewhere. So, that 0 is essentially what we call as the absolute 0. So, if I plot, for example, some temperature, the absolute temperature versus, for example, Qt by Q triple point. So, when Qt by Q triple point is essentially 1, okay. So, the slope of this is essentially y2 minus y1 by x2 minus x1. So, this is 1 minus 0. Then the y2 minus y1 is some temperature here, temperature of the triple point minus 0. What Kelvin also then assumed is that the value of the triple point of water, it is assumed to be 273.16. This is a way of making a scale. So, you can take that value to be anything at all. So, in this case it was said that let this value be 273.16 on some new scale. That scale is now what we call as a Kelvin scale. So, it was said that on this Kelvin scale, let us assume this value to be 273.16, the triple point. Then the slope of this line is also 273.16 minus 0 by 1 minus 0, which is 273.16 when you plot it as a T versus Q by Q triple point scale. The slope is this. So, this is how they came up with this new scale. one of the reasons for choosing this is that on this scale the melting point of ice comes out to be 0 degrees centigrade. So, when you want to use this to convert with existing scales, on this the melting point of ice comes out to be 273.15 Kelvin, which we are now taking as 0 degrees centigrade, and on this scale the boiling point of water comes out to be 373.12, which is very close to 100 degrees centigrade on the Celsius scale. So, that is essentially how this temperature scale was come up with. So, which we now use as the Kelvin scale. So, what we see is taken on this scale, Q1 by Q3 is essentially T1 by T3, because the scale is come up by the concept of running Carnot engines between different temperatures. So, whatever are the temperatures which are there are essentially the ratios of the heat transferred. So, we now have an absolute temperature scale where we define the temperature in Kelvin as 1 by 273.1, we define the slope as 1 by 273 of the triple point of water. So, if you take you can measure the triple point of water, because it is a repeatable measurement, because what you need to do is to have steam, ice and water, a mixture of this. You need to change the temperature and pressure in such a way that the proportion of steam, ice and steam ice and liquid water remain the same. So, we saw that this happens if you go to very low pressures and you go to low temperatures. So, when you get that kind of mixture and it remains constant, that is the triple point, and that is given the value of 273.16 on the Kelvin scale. And corresponding to that, you can plot all the other data, because if I was now to run a heat engine, so between any temperature T and the triple point, okay. So, if I was to run anything between T, some temperature T and the triple point, the ratios of the heat transferred would be essentially the temperature at T divided by the temperature at the triple point. This we are calling as 273.16. So, if I was to run a Carnot engine, I can measure the amounts of heat transferred and then find out the temperature. So, that is essentially how this scale was come up with. So, of course, we do not, so in theory we know how to make this scale. It is very nice because I have assumed this value, I now need to measure to heat transfers and I can find out temperature at any given point. But in theory, of course, we know that it is very difficult to make a Carnot engine, because we can't have frictionless devices, it has to be completely reversible and so on. So, what is more practically done is to make a scale using ideal gas thermometers, which is actually fairly close to the absolute thermometer scale. So, there is also another interesting thing with respect to the second law. If we look at the first law, we see that if you write the first law for reversible systems or even for irreversible systems, the first law is always correct. So, if we have heat transfer from high temperature to low temperature or low temperature to high temperature, first law will tell us how much is the heat transferred. But the first law does not tell us whether the heat transfer will occur or not. So, if I have a hot object in a cold room, what it says is the hot object will lose heat and its temperature will drop. Whereas, if I have an object in whose temperature is higher than the temperature of the room, the first law does not tell me that the temperature of this object cannot increase further. So, I have hot coffee I have coffee at 40 degrees in a room at say 20 degrees. First law does not tell me that the coffee cannot become 60 degrees if I just keep it there. If it became 60, the first law will tell me how much heat was transferred. I know that if I keep a 40 degree coffee cup in a room at 20 degrees, from experience I know that this coffee cup will come back to 20. First law says if this becomes 60, I can tell you how much energy was transferred, but it does not tell me it will not become 60. But the second law essentially tells us that in order to transfer heat from this cold temperature room to this coffee so that it becomes higher in temperature. This will not happen unless I do work. So, this is not a spontaneous process. So, having this coffee cup here, let us say it has this temperature at room is at say 20 degrees centigrade, coffee is at say 40 degrees centigrade. It says if I have this cup at 40, if I just leave it in a room at 20, there is spontaneous heat transfer and this will become 20 finally. So, finally my coffee is at 20 degrees centigrade. This is spontaneous and it will happen. If I have this coffee at 40 degrees centigrade and I have it in a room at 20, if I want to bring it to some 60, second law says this is not going to happen, because if I want this to become 60, what I want to do is transfer heat from the room to this coffee cup. Here I am transferring heat from the coffee cup to the room. This is spontaneous, but transferring heat upwards from a low temperature to this high temperature, according to Clausius, if I want to do this, I have to do work. So, which means there is something I need to do. This process will not happen on its own. So, in the first law, things are all symmetric. Things can happen in any direction, there is no problem. But the second law now it says things can happen only in certain directions unless there is some external intervention. So, spontaneous heating of the coffee cup of the coffee in cooler surroundings is not possible. So, what we see is that second law gives us direction to processes. The first law says everything can happen in any direction, but the second law says no, things can only happen in certain directions spontaneously. And we will see that in some sense our concept of time is linked to the second law, because things will only happen in a particular direction, and we will sort of elaborate more on this when we go on to what is called as Clausius' inequality in the next class, and then go on to the concept of entropy. Okay? So, thank you.